Hey everyone, welcome to this newest video. In this, we're going to be going over uniform circular motion, which is a type of motion involving objects going around in a circle at a uniform rate, so at a constant speed. It's got some pretty interesting applications and it's got some pretty useful formulas, so this is going to be a pretty useful kind of lesson. It's also a lesson people really dislike. Uniform circular motion is kind of annoying. I cut out most of the really annoying stuff from the course, so don't worry about like the cursed stuff, but we are kind of dealing with, uniform circular motion still a little bit. So, what in the world is uniform circular motion? Well, it's when you have a thing and it's going in a circle, sort of, right? But what it's supposed to be is a uniform circle. So usually we do a horizontal circle, right? It's when something's moving in a circle at a constant speed, right? At a constant speed, so this is uniform now, but if I speed it up, it becomes a different kind of uniform circular motion, right? It's also quite hazardous to do while not looking at anything with a mass on a string, so maybe I won't do that. But uniform circular motion is essentially when an object is moving in a circle at a constant speed. And it's a very special type of motion because it has some special rules and it also has some special cases, right? It's our kind of playing ground to deal with a lot of cool problems like kind of race cars turning or planets orbiting the sun or a bunch of other cool stuff like that. And we're going to approach it in two different ways, or we're going to learn it from two different ways. We have just done motion, right? And when we did motion, we started out by learning the equations of motion, which we would call the kinematics, right? We've got v equals u plus at, or s equals ut plus half at squared, etc. We had those kinematic equations. And then we also learned the dynamics. We learned the forces that give rise to those motions. And in fact, you could, if you did calculus, which we don't do in this course, derive the equations of motion from the dynamics, right? From the forces. We're going to do a similar thing here, obviously without the derivation again, where we're going to learn the kinematic equations that govern uniform circular motion. And then we're going to learn the equations of forces and stuff, or we're going to learn the force dynamics that cause uniform circular motion. So we're going to learn some new kinematic equations. We aren't going to learn any new dynamical equations because the dynamics is the same. It's still Newton's second law, right? But it's just going to be, different cases, and the forces are going to be slightly more tricky. So let's talk about uniform circular motion. The definition of it is when an object is moving at a constant speed, that's the uniform, right, around a circular path of constant radius. Okay, so it's a constant circle. Speed is constant and radius is constant. Notice I did not say velocity is constant because as someone goes around in a circle, their direction changes. And as their direction changes, so too is their velocity changing. So it's not constant velocity, but it is constant speed. Okay? So some examples. Driving around a roundabout. If you are like me and you're a nervous driver and you got stuck on a roundabout, you just kind of keep going and going and going and going and going. And you're just constantly going. Another one, NASCAR, right? I don't know anything about NASCAR, but they go around in a circle. I think they turn left. They go very fast and they go very left, to my understanding. You could also do a hammer throw, right? Spinning a ball on a string. The thing I was doing earlier, right? If I were doing it properly and and I wasn't worried about hitting everything around me, then that would be a good example of uniform circular motion. Other examples include cars taking a turn. We typically model that as uniform circular motion. And also the Earth orbiting the sun. Basically a circle, right? The Earth's orbit, so that's uniform circular motion to an approximation, right? A lot of these are approximately uniform circular motion, but that's good enough, right? It's just like how we were doing projectile motion, we ignored air resistance, right? It's like, well, we'll deal with what we can deal with because the non-uniform circular motion becomes like conic sections, and we don't want to do that, right? You don't want to do conic sections, trust me. So, let us first of all start to think about the kind of kinematics of uniform circular motion. We have, let's imagine, an object with a speed v, and it's kind of going around in a circle. The first thing I want you to know, and this is kind of self-evident, is that the direction of the velocity is always tangential to the circle. It's always along the circle. okay? So if the velocity, the velocity is always at a tangent to the circle, that's what that means, right? It touches the circle only in one place. What direction is the acceleration of the circle, of the object, right? Is it with the velocity? Is it against the velocity? Is it neither? Right? In fact, it is neither. It can't be with the velocity because then the object would speed up. It can't be against the velocity because then the object would slow down. And in uniform circular motion, we have a constant speed, meaning the magnitude of velocity is always constant. You should be clued in by the fact that when you spin something, you're holding it at the center. You're pulling it in towards the center. The direction of acceleration is what we would call radial, right? It's always towards the center of the circle because the acceleration is what gives rise to the change in the direction of the velocity. There is no change in magnitude of the velocity. And so let's talk about those magnitudes, right? The speed of the object, as we've said, is constant. It'll be v, right? V with no hat, right? So speed. It could also be u if you wanted it to because it's constant, doesn't change. But the acceleration of the object is also constant in magnitude, not constant in direction, but we'll deal with that later. And it has a specific formula. This is in your formula sheet, that the centripetal acceleration is equal to v squared over r, all right? V squared on r. It's just one of those things you remember that rolls off the tongue. We've got a here with a c. Now that c means centripetal acceleration. Okay, centripetal is center pointing, right? It's the word we use for the thing that makes the thing go round in a circle. So we'll have centripetal acceleration and we'll have centripetal force, right? And they are referring to the acceleration of the object as it goes around in a circle. And they're also referring to the net force on an object going around in a circle, okay? Now this, just like a lot of other stuff, actually already matches your intuition, right? So, one thing we say, if you are going faster, you need more acceleration to make a given turn, right? This should hopefully be in your experience. If you've driven a car, you're going real fast, and then you woof, you want to swing a turn around, you need to turn pretty hard. You'll experience a lot of force, right? You'll kind of move around in the car a lot as that vehicle turns. Similarly, if you go slow, right, the turn is very gradual. There's less acceleration acting on you. But also the wider the turn is, so the bigger r is, where r, right, is the radius of the circle. So if you're making like a turn like this, that's the radius there, r. It's the radius of the circle. It was about this much. Right? The bigger r is, the bigger the arc that you're taking when you turn. And if you've driven a car, it's easier to take a big arc than a small arc, right? When you take a small arc, you kind of skid around or you'll toss your passengers to the side or whatever it is that you do when you drive. But a wider R requires less acceleration. It's a safer, it's a smoother kind of a turn. So let's use that formula. Do you remember it? I hope so. A equals v squared over r. Now you're going to have to use that so often that it's going to essentially be tattooed on your brain. Like another formula coming up, g is equal to, f is equal to gm1 m2 on r squared, right? What is that? You'll find out, but it's tattooed on my brain. And g is 6.67 times 10 to the negative 11. You'll just learn that. We've got an F1 car. I don't know who it is. I don't know when it is either. I think it's Lamborghini. Yeah, a Lamborghini. I know it's Ferrari, don't worry. A Ferrari is doing a turn, right? A race car is approaching a circular turn of radius 2.34 meters. The car's tires can handle a maximum centripetal acceleration of 1.35 meters per second squared. What's the maximum velocity the car can turn at? So we write out our equation, we write out our known quantities, and then we search for our unknown quantities. So we've got A equals v squared over r. How do we know that's the formula we're using? Because it was just in the previous slide, right? But you're starting to realize, I hope, that we're starting to get many formulas that could be applicable to the same scenario. And so learning to triage, learning which formulas to apply and where is going to become a very valuable skill very, very soon. So we've got this. We know R and we know A. And we're looking for V. So V is equal to the square root of RA, which is equal to the square root of 2.34 times 1.35. That's not very fast. Whoops. Sorry about that. I should have done a faster one. Cool, and we square root that. Wow, 1.77 meters per second? That's so slow. You can run faster than that. Whatever, that's what I get for making up numbers. This is Ferrari slander. It's okay, Mercedes is a superior team. All right. It's not that easy though. There's a problem, or not a problem, there's a new world that we get to enter when we deal with uniform circular motion. That is the world of what we will call angular variables. So let's say you're imagining an object as it goes around in a circle, right? Like we have our object here. Now, if you wanted to refer to its velocity and you wanted to refer to its, say, position and a bunch of other stuff, you could plot it Cartesian, right? You could say, okay, your x value is this much and your y value is this much, and so on and so on. If you wanted to graph its motion, you could do two graphs in the x and y, and then, x and y would vary in some complicated function, a sinusoid, and then blah, 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 right? But what we're going to learn is that we can instead refer to the position of the object via its angular displacement, which is the angle theta it is from its starting point, okay? Right? Now, this angle theta, you pick an arbitrary starting point, just like how if you were graphing something, you pick an arbitrary starting point, like x equals 0 would be somewhere. And then theta is the angle at which the object is, right? So if it was over here, if this was the object, you draw this is the angle theta, right? Or maybe it's over here, and that's the angle theta, okay? But imagine we can use theta to refer to the position of the object along a circle instead of x and y, right? It saves us a bit of time, and it also lets us do some different maths, okay? So theta is what we would call our angular position. It's the angular version of displacement, right? So theta is the angular version of d, right? And typically they are vectors, right? Theta is clockwise or anticlockwise, right? D is, plus or minus or whatever it is. And that's kind of useful sometimes. And then it turns out that every single compound quantity, right? Angular momentum, every single quantity, I shouldn't have spoiled, has an angular version. So just like how we have angular displacement, we're going to learn that we have angular velocity and angular acceleration. And we need to know these terms in order to do some of the calculations that we get, okay? Now, before we begin, whenever you're using angular variables like theta, like in terms of angular displacement, whenever you're doing uniform circular motion, basically, the SI unit for angle is radians. And we're going to learn some formulas that only work in radians, not degrees, okay? Radians is just a way that works with the formulas that we have, okay? Degrees just doesn't work for some formulas, but radians does. So you should, when you're doing most circular motion problems, set your calculators to radians mode or hand calc it. Okay, to get a number in radians from a number in degrees, you multiply by pi, divide by 180, because a circle has 360 degrees or 2 pi radians. Okay, the radian is a very important term. And when we're using radians, then we can start to express angular terms. For example, we have this thing called angular velocity. Its unit is radians per second, right? It's the number of radians the thing moves every second. You could write degrees per second, right? That has the same meaning in that it's amount of angle per second, but it doesn't work with some of the formulas we're going to use, okay? So radians per second is the preferred way to go, okay? And we saw earlier, if you remember, that velocity is equal to change in displacement over change in time. So angular velocity is change in angular displacement over change in time. There's no angular time, don't worry, okay? Only the spatial dimensions are angular. Time is still linear to the understanding that we have. We're not gonna go there, don't worry. For example, a clock's minute hand completes one full rotation every 60 minutes. What is its angular velocity? Well, the angular velocity, omega, or W, if you want to be cool, is equal to change in angle over change in time. Now, our change in angle for one full rotation is 2 pi radians, right? That's one full rotation. And it was over 60 minutes. So that's 60 times 60, because we want seconds, right? And so we get here 2 times pi divided by 60 times 60. Wow, not much. 0.001745 radians per second. Now you might think, Tom, why am I learning this radian stuff? And yes, it's going to be useful in uniform circular motion here, but it's going to become really useful when we start to consider linear oscillatory motion in week 4, okay, and in week 5. It's going to become very, very relevant to be able to use these radian units and these things like omega. There's a lot of physics that is built on angular variables instead of linear variables. And unfortunately, or fortunately, I've got to teach it to you. Now we've got linear / tangential velocity. So the question is, how does the linear velocity relate to the angular velocity? I say linear, this means tangential, right? At the tangent to the circle. They're the same thing, okay? It's this. V equals r omega, okay? Where r is the radius of the circle, as long as omega is in radians per second, okay? When you multiply in the radius, you've got to be in radians. That's the rule, okay? So, the minute hand from the previous page, if we remember, it was omega is equal to 0.0017 radians per second. What is the tangential or linear velocity of the tip of the minute hand? This part right here, right? One thing I want you to appreciate is that the tangential velocity of various positions on an object is not the same, right? The linear velocity, sorry, the rotational velocity of every single point on this pipe is constant, right? They all rotate the same amount of times per second, or they all take the same amount of time to do one full rotation. But the parts on the end, by virtue of having a larger r, a larger radius, are going to have a larger linear velocity, right? This moving to here is more move than this moving to here, even though it takes the same amount of time. And therefore, the ends of this pipe have a much larger linear velocity, right? That's why when you hit a baseball or something, you want to be hitting it with the further out you hit it with, the kind of faster your baseball bat is going, right? Or cricket, or whatever. I don't think we can do a cricket from here. You can't see it. So we've got our linear velocity is equal to r times omega, which is 0.1 because we would always use meters, times 0.00175. I wonder what that is. It's 0.000175 meters per second. Slow. Of course it's slow. That's a clock, right? Takes a long time to tick. There are some other formulas that aren't really examinable because they're not in the formula sheet, but they're really useful, right? And the thing is that you can derive them, but I'd recommend just knowing them, okay? The first one is here, AC equals R omega squared. So this is AC equals V squared on R, and then we take this and we put that in there. So then we'll get R squared omega squared on R, which is equal to R omega squared. Okay? That's centripetal acceleration in angular terms instead of in linear terms. Right? Useful sometimes. We've also got this, the definition of velocity, linear velocity, for an object undergoing uniform circular motion. Right? Because 2 pi r is the distance for one rotation. Right? It's the distance traveled over one rotation. And t is the period of one rotation. And so what we get is one divided by the other to make our velocity. Right? It's another way of finding the velocity. Right? Instead of using v equals r omega or some other form. Now what you're going to realize is when you deal with angular problems like this, there's probably going to be 3 or 4 ways to find the same number. That's great. That's physics working, right? Because physics is physics, there shouldn't be just only one way to figure out a certain physical quantity, right? There will be multiple ways. And this is something we're starting to see when we deal with angular variables. So let's try an example before we move on to forces, which is the dynamical side. A centrifuge is used to train astronauts to survive high amounts of acceleration. We have a centrifuge here with a radius of 15 meters. At what angular velocity should it be given if we want the acceleration to be 3 times Earth's gravity? So what we're looking for is AC is equal to 3 times g. And we have r equals 15. And we have omega equals something. We're looking for the angular velocity. We're not looking for the linear velocity. So we will do AC equals r omega squared. Now that's not examinable. That's not in the formula sheet. So we could do AC equals v squared over r and v equals r omega and then combine the two. Right? Because these two are on the formula sheet, so you could be expected to do it in 2 different steps. But we're doing it here in 1 step, because I remember the formula. And maybe in your exams, you'll remember the formula. That would be nice, wouldn't it? So we're looking for omega. Omega is going to be equal to AC over r, all square rooted. And that is going to be equal to 3 times g. So I'll write it as numbers. 3 times 9.8 divided by 1.5, all square rooted, which is 4.42 radians per second. That's insane. That's really fast, right? That's almost 1 rotation every second. Scary. But that's it. That's a pretty simple calculation, right? So that's kinematics for rotation. In the next video, we're going to go over dynamics of rotation. We're going to look at forces. Centripetal force. It's not a real force, but we're going to look at it anyway. So thank you for watching this video, and I hope to see you in the next one.